Hello, everyone. Welcome to the SK Goshen Associates session on high-rise building design. My name is Larry Novak. I'm a licensed structural engineer, and I certainly say that with pride, especially with this group. Now, there are many types of high-rise buildings and many types of systems. We're going to discuss some of the systems. But what we're going to discuss primarily today is things that they all have in common. One of my mentors when I was at Skidmore, Owings & Merrill was a man named John Zills, great engineer, Sears Tower, John Hancock Center. And he used to always say, never run an analysis unless you already know the answer first. And at first, when I heard that, I thought it was a little crazy. But now, having done more of my career, I understand that that's an important part of back of an envelope hand calculations. So you can avoid the garbage in, garbage out. You have a feel for the answers. And additionally to being a licensed structural engineer, I'm a fellow of the American Concrete Institute, a fellow of the Structural Engineering Institute, a LEED accredited professional. I'm also a full voting member on ACI 318, the concrete standard, as well as ASCE 7, the standard on building loads. Being on both sides of the coin, the loads and the design side, gives a unique perspective and contribution. So things that we're going to discuss today, we're going to talk a little bit about the history of high-rise development and how the materials that have changed also affected that. We're going to talk, more importantly than design, the behavior of high-rise structures. I've always learned that behavior is critical to understanding the design. The design code equations may vary by whether you're using US codes, Euro codes, other codes around the world, but the behavior will not change. So we're going to understand the behavior of what we're doing. And we're going to have a special session at the end on how to avoid pitfalls, where we're going to discuss about some of the challenges that can develop and how to avoid them at the schematic stage. And we're even going to add a section on foundation design, which was one of the comments we received back from the last time we talked about it. So we're going to talk about mat-supported foundations, which are very common for tall buildings. So basically, of course, building is human nature. We all want to build taller. What you see a picture on the left is a picture of my daughter. And stacking blocks, we all did that when we were young. And believe it or not, we started to learn intuitive things about load path and even aspect ratio, height to width. And we discovered if we want to put more blocks on top, we needed more blocks on the base, a lot like the pyramids. And I often say as a structural engineer, I'm just still a big kid who gets to play with really big blocks. And one of the keys of tall building design is never make it more complicated than needed. My dad, also a structural engineer, said the 3 rules of structural engineering for tall structures is constructability, constructability, constructability. When we do low-rise structures, we have a lot more options to do random walls or unusual layouts. But when we do a tall building, we have to have a dedicated system that we can almost draw on the back of a napkin to explain it to someone. We can't have what I'll call push-button engineering, where it only works because the computer tells us it works. We have to be able to understand the load paths. And surprisingly, this is extremely hard to do, because making something simple is the hardest thing to do. Having a dedicated thought from the beginning of a project is a challenge. But on a high-rise building, it's important not only from the structural system, but for the architects to understand how floors to floors will change, how the contractor will build it. All those aspects need to be coordinated in at the beginning and not say they'll be decided later. Even the mechanical systems and the risers become a critical part, and we'll discuss that even more. And we talk about structural engineering, and the majority of the people online are structural engineers. I've often searched for a good definition of structural engineering, and this is the best one I found. It was penned by Eric Brown in 1967, and surprisingly, Eric Brown was not a structural engineer. He was an aeronautical engineer looking at our profession. And he said engineering, specifically structural engineering, is the art of molding materials we do not really understand. Do we look at the concrete breaks of cylinders? It's a shotgun. How does concrete even break in flexure? Very confusing. Even structural steels have different behaviors between fracture and fatigue. Into shapes we cannot really analyze, and we're getting better at that. We're getting better with our computers, but we really don't analyze creep and shrinkage perfectly yet. We certainly don't know everything that's going on inside a wall.